Hello, my name is Jonathan Russer. Today we'll be talking about the red herring attack, testing the reliability of attack detection, paper accepted at EMNLP 2025. So first, a brief motivation of why this research is interesting, what motivates this type of attack. So for text classification purposes, often we have our text classifier, which simply will take in a piece of text and assign it a label. So this label, in this case, we have this negative text going in, and so the text classifier here simply examines it and gives it the negative label. Normal attacks work by modifying this text in such a way that it still reads the same, has the same sentiment in human eyes, but causes the classifier to misclassify. So in this case, still reads negative here after being modified by the attacker, but the classifier misclassifies it as positive. Now, in response to this, there have been defenses such as attack detectors proposed, which also take a look at the same text and try and determine if it's been modified by an adversary or not. Essentially, is it attack or not? So attack, it's been modified by adversary, not, it has not. And what can be nice with this is now that we have both a classifier, which is getting targeted and doing the main duties of classifying as positive or negative, we have a attack detector, which acts as extra security and flagging different text on attacked or not. We can have a human then moderator look and see when certain texts are being labeled as attacked by this attack detector. And this can cause then humans to notice there's something wrong with this text, especially because the classifier is misclassifying it. Therefore, I'll manually moderate it or apply some extra security measures on top of it. Now, how does red herring attack differ from these traditional attacks? Well, red herring, rather than trying to make the attack detector or the original classifier fail, it focused on the attack detector. And specifically, it tries to pit the classifier against the detector by modifying text in such a way that the classifier still classifies correctly, but the detector is saying an attack is happening. So what happens then is the human sees an attack is supposedly happening, they examine the text and the output from the classifier, and they see that in the classifier's eyes, it's classifying correctly. So this must be a false attack being noted by this attack detector. And the issue that this can cause is over time that if a human keeps seeing that this attack detector is giving false, in its mind, false flags, it's saying attacks are happening when clearly they're not because the classifier is still classifying correctly. Then they can cause mistrust on the classifier, which cause issues of companies abandon these entirely and cause security issues. So red herring has three main goals. One, make the detector say an attack is happening, while two, at the same time, making the classifier still predict the correct label, and three, the text still should be the same to humans. That way, there's this mistrust that's created between humans and these attack detectors. So let's look at a little more detail of the red herring approach. So there's two main steps to it. First, we're trying to find where we'd like to insert a new word within this text to modify, and second, which word should we actually insert. So for the first step, we use a common technique called greedy select, where we're simply removing words and trying to find which words, remove them one at a time with replacement, and we find which ones is the classifier relying heavily on to make its classification. After we do this, we then have a list of which words the classifier is relying the most heavily on by looking at the drop in true class probability. Now it brings up the question, why would we look at the classifier, not the detector, since we're attacking the detector? Well, for many cases, the attack detector is actually looking at the classifier for feedback as well. So the detector often will look at the outputs or probabilities of the classifier to make its decision whether an attack is happening or not. And so by targeting the classifier and getting feedback from that, we're essentially also undermining the attack detector at the same time. Second step is now we're trying to find which word insert. So now we insert a word in front of those words we've got from step 1, and we use a masked language model to do so. So the masked language model is able to look at words where we insert masked tokens and give us suggestions for that. So after we get these suggestions, we look for feedback from both the classifier and the detector with their goals in mind. So first, we want to make sure the detector is saying an attack is happening. Second, we want the classifier to get the true or gold label. And if we find a word that gets both of these, we stop there. Otherwise, we keep repeating this process over and over, keeping the ones that are more likely to have an attack being flagged and less likely to cause a misclassification for the actual classifier. So which attack detectors do we examine for this research? We look at three mains: one, FGWS, WDR, and UAPAD. FGWS uses synonyms to help determine if an attack is happening. WDR removes words and looks how the classifier reacts when that happens. And UAPAD has its own perturbations it adds in to determine if attacks are happening. We run these class detectors on 4 different data sets, 4 standard ones for attack in the attack research space, and 5 different variations of classifiers. And results we see here are just the standard, how the different detectors are performing on these original data sets. Now on to RedHerring's results. We have a large table here where we attack the different detectors, and we also then look at how the classifiers change when those detectors and the different combinations of the classifiers are examined. So there's lots of things we take away from this. We'll highlight the main ones here. The rest will be in the research itself. So the first big one is RedHerring is successful at dropping the attack detection accuracy. So we see these averages here across the different classifiers, and for all of them, especially the FGWS, but all of them see a drop in detection accuracy, which means they are falsely saying an attack is happening when it's not. That's the first goal. The second goal is the classification accuracy is maintained or improved. So we see these negative values here, which means actually it's doing better on these texts that we give it, the classifier. And so we see this big contrast between the classifier and the detectors, which will have the humans mistrust the detectors even more. Finally, we ask humans to determine if an attack is happening or not on the text and the classifier and detector output, and we find that humans agree with the detector far less when against RedHerring text compared to standard attacks or non-attack text. Now we also want to investigate, can we defend against this? We run a couple experiments for that. We look at 2 main ones. One is adversarial defense, which are standard. The other is a defense we proposed. So for adversarial defense, we find that there is slight improvement when we use adversarial training, but there's still this large gap in how effective RedHerring is against these. For our proposed one, we propose a confidence threshold where we look at, well, what is the confidence of the classifier? And so if it's a high confidence and the detector says there's an attack happening, well, then we say attack's not happening. However, if it's low confidence and the detector says an attack is happening, then we say an attack is happening. And so we find around this trade-off of C around 0.9. We see that for regular attacks and RedHerring, we find a good trade-off on actually getting correct predictions for both the classifier and the detector. So that brings us to the end of our talk today. There's a lot more other results within the paper itself. Specifically, what if we only focus on the detector, for example? There's other automatic evaluations of the text and even more in the paper. Thank you.